Okay, so we're going to now learn how to solve exponential and logarithmic equations. So the basic idea is we have some expression, a logarithmic or exponential expression with an unknown variable x, and we want to solve for x. But we can't just use addition, subtraction, multiplication, division like we did in algebra. So we've got to use the properties of logarithms and the fact that the exponential function e and the natural log are inverse functions. So more explicitly saying that, there's two ways. It says both exponential and logarithmic functions are one-to-one and have one-to-one properties. So the property, so what this says is the other method is if you have two expressions that are equal to each other with the same base, then we know that the exponents have to be the same. And that's because it's a one-to-one function. For every value of x, there's only one value of y. For every value of y, there's only one value of x. So that allows us to be able to make this conclusion. So this is the exponential form where you have the same base. And the same thing is if you have logarithms to the same base, for these to be equal to each other, y has to equal x. So if we can get them in this form, then we can change it from a logarithmic expression into just a simple algebraic type thing. And the second one is using the inverse properties of logarithms. So if you have a raised to the log base a of x, because they're inverse functions, f of g of x equals x, and the other way around, g of f of x equals x. So we can use that sometimes to help us solve these. So the strategy, and it's on the bottom of page 225 in the 6th edition, is you rewrite the original equation in a form that allows the use of the one-to-one properties of exponential or logarithmic functions. So that's using, if we can get it in this form, then we can just set x equal to y. You can rewrite an exponential equation in logarithmic form and apply the inverse properties of logarithmic functions, or you can rewrite the logarithmic equation in exponential form and apply the inverse properties of exponential functions. So that's using this technique. So let's just go through some examples. So here we have 3 to the x equals 729. So we want to solve for x. So one way is to rewrite 729 as 3 to the 6th power. And as a consequence, because we have the same base, then we can say that x equals 6. Okay, so that's the easy way. That's if you recognize that 729 is 3 to the 6th power. That might not be always so obvious. So there another way of doing it would be to take the natural log of both sides of the expression. Just use your calculator method. So I'm taking the natural log of both sides. I could take log base 3, but it turns out that it doesn't really save us that much time, and it's just easier to deal with natural logarithms. So what we've done is we applied the same function to both sides. So they should still be equal to each other. And then we can bring the x outside the expression using the exponential property of logarithms. And then we could just solve for x. So it's equal to the natural log of 729 divided by the natural log of 3, which you can plug into your calculator. And if you do that, I know the answer is 6. So if what you do is ln of 729 divided by ln of 3, which is 6. If I had done log base 3 of x, 3 to the x, and log base 3 of 729, you bring x out, you get x times log base 3 of 3. Here we have log base 3 of 729, but I don't have that in my calculator, so then I could use the change of base formula to do that, which is the same thing that I got over there. Okay, so again, if we can rewrite this as, if we can take 32 is equal to 1/2 raised to some power, then we could do that. Now we know that 2 to the 5th power is 32. So you might think that 2 to the minus 5th power is, or 1/2 to the negative 5th power. Let's see if I had 1/2 to the negative 5th power, probably is 32. Just because I've taken the reciprocal of this and I've changed that to the negative. So if that's true, which I think it is, what you could do is you could say it's 32 is 1/2 to the minus 5th power. And now I've got the same base, so I could say x is equal to negative 5. That's one way of doing it. The more straightforward way is, again, use the natural log of both sides. So again, I can pull that variable out. And I can solve for x. X equals the natural log of 32 divided by the natural log of 1/2. And I can plug that in my calculator. Natural log of 32 divided by the natural log of 1/2. And I get negative 5. Okay, here, all I really have to do is move this term to the right-hand side. And because they're both the natural log, you can say x equals 5. So I think that's the only one I'm going to show for that one. I don't know why I have these two. I think just to show you how you solve them. So in this case, you could use the inverse properties of the exponential and the log. So what I'd do is I'd take each one of those sides and make them the exponent. And then e to the natural log of x is just x. So the answer is e to the minus 7 power. And over here you can do the same thing. You can do e to the log base 3 of x. And that doesn't work though because the bases are different. So that what you would do here is you would say 3 to the log base 3 of x is equal to the same as 3 to the minus 7 power. And because these bases are the same, you can use the inverse properties. Just say the left-hand side is equal to x, and the right-hand side is just 3 to the negative 7 power, which is going to be a really small number. 3 to the negative 7 power. Well, it's not as bad as I thought it was. It's 4.572 times 10 to the minus 4. Okay, here we want to solve for this part. Log base 10 of x equals 2. And so it's the log base 10, so using the inverse properties of logarithms and exponents, I'm going to choose 10 as my base. Then I'm going to raise both of these to 10 to the log base 10 of x is just x. So the answer is 10 squared, which is 100. 10 times 10. If you plug this in your calculator, because you can do this, log base 10 of 100 minus 2. Well, log base 10 of 100 is 2. So you do get the right answer. Okay, so we're solving for x, so we got to isolate 5 to the x, kind of like we used to solve for x, but we have one more step you have to take. So we divide both sides by 2, so we'd get that. And now we want to solve for x. So when you're going from logarithms, when the variable is in the logarithm, then you typically have to choose the correct base to match the logarithm. But when you're doing exponential functions, you don't have to use log base 5. You can just use the natural log, and that's the easiest thing to do because it's in your so readily available in your calculator. So I take the natural log of both sides. Then I bring x out, and then I divide by the coefficient in front of x. So there I get natural log of 16 divided by the natural log of 5. So I get 1.7227. And again, you can check that out. So if you take 2 times 5 to the 1.7227, let's see what we get. So 2 times 5 raised to the 1.7227 power is 32, approximately 32. Okay, again, want to solve for this e to the x, so we just have to add 9 to both sides, like that. It's an exponential function. In this case, it is e, so that makes it even easier. So I take the natural log of e to the x, natural log of 28, natural log of e to the x is x, and then I just plug in natural log of 28 in my calculator, and I get 3.3322. Okay, so this one was already solved for some base raised to some power, so I don't have to do anything like here I had to divide by 2 first. Here I had to add 9, but it's already by itself, the power. So I'm going to again use the natural log of 8 to the minus 2 minus x power is equal to the natural log of 431. So this is the exponent, so I can bring the whole thing out in front of the logarithm. Then I can divide both sides by the natural log of 8. Then I can add 2 to both sides. Make sure you don't say the natural log of 431 over the natural log of 8 is the natural log of 431 over 8. It's not going to work. And so x is equal to negative 2 minus the natural log of 431 over the natural log of 8, which I can now just plug into my calculator. So we've got negative 2 minus the natural log of 431 divided by the natural log of 8, and I get x equals negative 4.9172. So if I evaluate 8 raised to the negative 2 times negative, and then I put a negative 4.9172 here, that's the same as 8, and so you're adding the 4 really, so it's negative 2 plus 4.91721. That's 2.91721, and so 8 raised to the 2.91721 power is 431.03. So again, that's just because I didn't take out an infinite number of data points. Now this one's tricky. What you have to realize is you can factor this. So what you would have is e to the x here and e to the x there. So when you multiply them together, you get e to the 2x. And then one is going to be negative and one's going to be positive. I'm going to make the 5 negative and the 1 positive, so that I get negative positive 1 times negative 5, which is negative 5, and then I'll get negative 5 plus 1, which is negative 4. So at that point, just like normal factors, if this factor is equal to 0, then the original expression is equal to 0, and the same with the second part. So what I do is I take e to the x equals -1, and I get e to the, and this is actually positive 5 here, so it's e to the x minus 5 equals 0, or e to the x equals 5. In this case, if I take the natural log of both sides, the problem here is you can't take the natural log of a negative number, so that's not going to work. So we have this side, and so what we get is natural log of e to the x equals the natural log of 5, or x equals the natural log of 5, which is, what is the natural log of 5? It's 1.609. So you get x equals 1.609. So let's just check it out. X times 1.609 minus 4 times e to the 1.609 minus 5 equals something. So let's just do it on a calculator. E to the 2 times 1.609, and I did something wrong there. There we go. 2 times 1.609. So that's 24.978. Then I've got -4 times e to the 1.609, which is minus 19.992 minus 5. It should equal 0, or close to it. It's not going to equal 0 exactly, because my answer is only to 5 decimal points, but I get negative 0.014, which is approximately equal to 0. Okay, here we need to solve for e to the negative 2x over 3. So I divide both sides by 8, like that. Then I take the natural log of both sides, again using the properties of logarithms. So the natural log of e to that is just negative 2/3 x is equal to the natural log of 11/3. Let's do that. Natural log of 11 divided by 8 is 0.3185. So x, so I multiply that by 3 divided by 2, and I get negative 0.4777. So again, I can check this out. 8 times e to the minus 2 times negative 0.4777 divided by 3. Let's try that in my calculator. 8 times e to the negative 2 times negative 0.4777 divided by 3. And I get 11. Okay, this one's simple. E to the natural log of x equals e squared. E to the natural log of x is x, so it's equal to e squared. Okay, so let's continue on. So again, we're solving for x. It's a logarithmic expression, so there'd be two ways. If we had both sides were log base 10, then you could just set the arguments equal to each other, but in this case they're not. So so convert a logarithmic expression to get the x out of side of the logarithmic expression, we use the exponential form. And to do that, we have to use 10 as the base. Like that. So each side becomes the exponent of the exponential function. So 10 to the log base 10 of x is x. And so we just get 10 to the 6, which is 1,000,000. I was trying to think if you could, what would happen if I did this? If I said e to the natural log of, or to the base 10. So this is not the easier way, so I'm just thinking about this. So if you had e to the log base 10 of x equals e to the 6th power. Now the problem is that these don't, these are both not e to something. So what you could do is you could rewrite this as the natural log of x divided by the natural log of 10. This side stays the same. And let's see. What I was thinking was, yeah, I'm not sure how you do that, so let's just ignore that. Okay. So here we have the natural log of the square root of x plus 2 equals 1. So again, we need to get this outside of there. So the first thing we'd probably do is we would rewrite the square root as to the 1/2 power. So we do that, and then you can bring the 1/2 out. And then we could multiply both sides by 2, so we get this. That. Now, just like over here, we had log base 10, so we do e to the natural log of x plus 2 is equal to e squared. E to the natural log of x plus 2 is just x plus 2. So you get x is equal to e squared minus 2 if you solve for that. And let's just plug it into the calculator, then we'll check our answer. So you got e squared minus 2, so that's 5.389. So e squared must be 7.389. So now if we plug that back in, the natural log of the square root of 5.389 plus 2 equals the natural log of the square root of 7.389. So let's do that on my calculator. The natural log of the square root of 7.389. And I get 1, which is the right answer. Okay, so here we have, we've got x in the numerator and the denominator. So again, just like the previous problem, we start with a logarithmic expression with the argument containing x. We have the same kind of thing here, except we have x twice. So we would do the same thing. We do e to the natural log of x over x plus 1 equals e to the 2nd power. E to the natural log of something is just something. So then if you multiply both sides by x plus 1, you get that. And then you multiply out the right hand side, so you get e squared x plus e squared. Move the x's to one side, so you'd have x minus this term. Factor out x. 1 minus e squared is equal to e squared. So x is equal to e squared over 1 minus e squared. So we get e to the second power divided by 1 minus e to the second power. Should be a negative number. Negative 1.1565. And let's just check that out. So the natural log of negative 1.1565 divided by negative 1.1565 plus 1. So you're going to get a negative in the numerator and the denominator. So it ends up being positive. The natural log of 7.3899. And you get 2, which is the right answer. Okay, solving for x again. So we're going to have to use the properties of logarithms to put all this stuff together. So if you move all of the stuff to the one side, so this moves to the other side, so it becomes negative. That equals 0. And there are no coefficients out in front of those, so we don't have to bring them in. We just have to combine these. So you have log base 2 of x times x plus 2 divided by x plus 6 equals 0. Then you would say 2 to the log base 2 of x times x plus 2 divided by x plus 6 equals 2 to the 0 power. 2 to the 0 power is 1. Any number to the 0 power is 1. And on the left-hand side, 2 to the log base 2 is, using the inverse properties, is just x. And I'm going to go ahead and multiply this out. X squared plus 2x divided by x plus 6 equals 1. So that's the right-hand side. So we're going to end up with the quadratic equation here in a second. So multiply both sides by x plus 6. So x plus 6 times 1 is x plus 6. Move this to the other side. So you get x squared plus x minus 6 equals 0. So when you subtract x from both sides, this goes to 0. X, so this is 2 minus 1 is 1. 6 comes to the other side, becomes negative, and you can see I can factor that. So it's x plus 3 and x minus 2 equals 0. So x equals negative 3 and x equals positive 2. Now the question is, can I use either one of these? Does one get eliminated? Well, if you go back to the original expression and you plug in x equals negative 3 here, the domain is x has to be greater than 0 for this one to be greater. If it's 0, if you put 0 in here, this will be okay. 0 plus 2 and 0 plus 6, but this one, log base 2 of 0, does not exist, so this one is not going to work. So the only solution is x equals 2. So let's try that. Log base 2 of 2 plus log base 2 of 2 plus 2, so I'm going up here, plugging in, is equal to log base 2 of 2 plus 6. Well, the log base 2 of 2 is 1. The second one we have is log base 2 of 4. And on the right-hand side, we have log base 2 of 8. But log base 2 of 4 is, this is 2 squared. This is 2 cubed. So you can bring those out. So it's 2 log base 2 of 2 is equal to 3 log base 2 of 2, but log base 2 of 2 is 1. So that works. That looks like what I just did. Okay, so leave that off there. Okay, so those are some examples, and we'll do some more in class, get you some practice. Now we have a couple of word problems. This is says that the forest yield has the relationship V, the volume of material, is equal to 6.7 times e to the minus 48.1 over t, where t is time. And you can see as t goes to infinity, you get e to the minus, well, you get to the negative 0 power, because you get a number over infinity, so this goes to 0. E to the 0 is 1, so the yield levels out. So it actually doesn't look like this. This is kind of, that's the way you'd think an exponential function would look, but it doesn't look like that in this case. So that's at t equals infinity. At t equals 0, you'd have 6.7 e to the infinity, right? Because you plug 0 in there, and you'd have something over 0. It's actually minus infinity. So this, if this is infinity, t is infinity, the argument is negative infinity, which is e to the minus infinity is 0. So you start off with 0, and then you grow. So it must look something like, probably something like that. I guess. I don't know. Just I mean, there's really only two possible. Well, you could say, well, it could go like this, but I don't think that's what it does. And I'm really not sure what the question is. So. Oh, okay, so that's what it looks like. So it doesn't. It's kind of a combination of these two. So it starts off as 0, then it grows rapidly, and then it ends up leveling out. Okay, I guess that's just to show you how the thing is drawn. I guess the thing is, you know, if it was e to the minus t, yeah, that's the reason. If you did, you know, e to the minus t, it would look something like, it would look like that. And if it was e to the t, it would look something like that. But this is 1 over t, which gives you this other more interesting picture. Okay, then we have this expression which shows the temperature of an object in a room. So the temperature of the object is 160 degrees C, and it's removed from a furnace and placed in a room 20 degrees C. The temperature of the object was measured each hour h and recorded in the table. A model for this data is t equals 20 times 1 plus 7, 2 to the negative h power, where h is the number of hours. And you can see as h goes to infinity, you get 2 to the negative infinity. And remember, exponential functions look like this, go like that. So, and that's the argument. So as the h becomes large, this is what we're plotting here is negative h. And so this is going to approach 0, and so you get 20 times 1 plus 0. So it says as t goes to infinity, or h time goes to infinity, temperature goes to 20, the room temperature. And the way this thing actually looks is something like this as a function of h. This was a function of negative h. So it starts here at 160, and then it levels out at 20. So here's a plot. If you plot these points, 160 at 0 hours, 90, 56, so forth. If you draw a horizontal line, you can see this thing approaches it. So that's what it actually looks like. And what I'm doing here is showing how you would solve this in Excel, which I think I'm going to do in a separate video. And there's your homework assignment for this section.